All right, how's it going, everybody? Hope you're having a good one. I had an inspiration from Craig Miglaccio. So he recently launched his online course platform as well. He's focused on fundamentals, basics, residential, light commercial, things like that. Highly recommend you go check it out if you're curious, if you want to learn more about that stuff. But he did a fun, what I thought was fun, like Q&A video, and I realized like I haven't really done something like that for myself. So today we're gonna just open the stream. It's not gonna be the whole stream. We're gonna get into our normal questions and stuff. So feel free to go ahead and get those in the chat and start adding whatever questions you have, chiller related. You don't have to. It doesn't have to be specific to the cert course. Okay. I'm just gonna go through some of the routine questions I get. I'm gonna kind of talk through them. I also plan to actually go in and show you a bit of what is in the course itself and just kind of what it looks like, what you would expect that experience to be. So we're gonna just have a few minutes here. I want to go through it for a little bit, and then we'll dive into the other questions. I still have plenty of questions on reserve as well. So hope everybody's doing well, having fun. By the way, before we dive into it, let's see, we got him in the chat here. I've really been getting into the RTAF and our ACR series. It's coming really choppy. I look good on my side in terms of stream signal. Audio shows good. Yeah, I'm sorry, but on my side, I don't. All my monitoring stuff says what I can do. I'm currently doing. I'll keep an eye on it. Hopefully, it improves. Um. Anyway, really interesting stuff coming out from Train. I do plan to talk about that very soon. I'm not ready to really dive into it this week, but once I have kind of finished going through everything, I do plan to jump on the stream and do a full, um, like, let's see, do a full top to bottom of what I've been researching with how they're doing oil recovery circuit and their little brace plate heat exchanger they have in there to the thermal siphon. Really interesting stuff. Let's see. I'm kind of playing with the video feed now here. Interesting. Let me check one setting real quick. Make sure. Just want to make sure I'm not having any kind of something easy I can resolve. Let's see. That looks good. Yeah, that looks good. Yeah, there's nothing obvious on my side. Yeah, we'll just have to roll with it, and I apologize if it's ever for everybody, if it's causing any problems. Anyway, with that, let's just roll into one of the first common questions. What is this thing? So my certification course is built to be, I like to refer to it as like your senior tech in your pocket. The role of a senior tech has always been, or not always, one of the roles is to be a mentor and a guide and a field trainer for technicians. And that's not been the, it's becoming less and less the case. It's the same on both videos. It's becoming less and less the case with the modern industry because the senior guys have just retired. So our workforce has decreased or is at minimum maintaining. It's not actually growing all that much, or not to the scale that it needs to. We don't have the senior guys to replace the ones who we have lost. In addition to that, our industry has grown so much that we don't have the technicians we need. Period. That what that leads to is we're spread extremely thin. So we're in in historical reference, you would work with a senior tech for quite some time before you ever got to go work on stuff yourself in the field. And while this is true in some places, still there are some places that have been able to maintain this. Most haven't. Most of the time, you get just enough training to get released out there, and then from there you're just cut loose and expected to figure it out. And it really puts the apprentice in a very difficult position, because now they're trying to go out and figure out how they're going to just work through this. And that means you're having to constantly make more phone calls. It means you're having to constantly try to look things up more. So the point is, this course is built in a way to where it's meant to go with you in the field. It can be used on any platform, any device, any of that kind of stuff, but it's meant to go with you in the field. It's meant to where I want you to literally, as you're standing in front of your machine, pull up. Like, if you're seeing issues with a screw compressor and you're really trying to get your head around it, pull these images up. Come in here and look, or go through the lesson. Let me explain it to you while you're there, while you're looking at it. I also have an MP3s in here to where if you need to do like a podcast, or if you can't get the video, maybe you're down with a very bad signal, you just need to hear me explain something specific. You can do the audio form. You don't have to do the full video, so it loads better. And these are MP3 specifically because they're very small, easy to load files. And that's why I didn't do some of the higher formats, because they're just too big of a file. And the whole point of this is to be accessible. And then you can roll through and see these different examples and visualize what it is you're trying to work on while you're there trying to work on it. And so the whole goal here is to just be there to support, to give you that information, to give you a comment section that you can go into. This particular lesson doesn't have any. Let me see if I know we've got a few that. Let me pick a good one. Maybe this one. Let's see what kind of comment. Yeah, so like you can go in and see what other people are saying, what their opinions are, what the questions are they're asking. You can get that additional feedback. Really love to pick one. We've had some of these lessons in particular that have some really good conversations going on. I don't remember which one it was. Anyway, like that's the whole point of this, though, is you can go through, and all this is broken out into its specific components. And I intentionally made this to where each lesson was less than 30 minutes. None of these are more than 30 minutes. As you can see, a lot of these are less than 10 minutes. That's because I'm not trying to bore you to tears with all the little nuances of everything. What I'm trying to do is give you the specific information that you need to make the correct assessment and understanding in the field quickly. Like, I want you to truly understand this from a technician perspective. It's one of the issues I have with a lot of the factory training is it's all broken down, and sometimes they're just going way off into the weeds on certain things that just aren't really needed for it, especially if you're new to this. That's some of those things you can absolutely learn as you get deeper in, and it's useful, it's helpful, but some of it is just not yet. We're not quite there yet. Yeah, I do see the comments, the voice is breaking. I do apologize. I'm not sure. Everything on my side says it's supposed to be functioning. I don't know if YouTube is struggling. My connection and everything looks really strong on this side. I'm assuming it's got to be on the YouTube side. Normally, if I'm having issues with me, so I've got a whole set of tools here that I can monitor the stream feed. All of those say we're good. Anyway, so that's what this course is really meant to do. It's meant to take you literally from square one of no, not that one. What is a chiller? Right? That's quite literally the very first question, the very first lesson that we start with. What is a chiller? Right? And I give you some examples of just what these machines are going to look like. We've got a quiz we can go through. I'm getting bullet points added for like lesson summaries you can go through and read. And then we get into, so this one's got a pretty good chat. We get into the comments where you can ask more questions, give some feedback, or just share what you've been taught and learned. And from there, we build on this: air cooled, water cooled, hydronics. Why even be a chiller tech? Um, and then, we progressively just continue building into a whole module on air cooleds, their design, their sequence, their water cooleds, into scrolls, recips, screws, and then we get into centrifugal. So, yeah, the core, going back to the core here, this is the purpose. It is to create a industry standard in a place where we can come together, we can learn as a collective, and have a very clear understanding together. And I take all the nuances that the manufacturers have, and I just smooth all that out. What I mean by that is they call things commonly by their own terms, many of them. And so I'll give an example. A PRV with a York centrifugal is an inlet guide van. It's an IGV. Just York is the only one I've seen to call it a PRV, but they're saying the exact same thing. But again, if nobody's told you that or if they haven't explained it, that may not be obvious. Same thing with VSD. So these manufacturers will get into this thing of, I want to have a special name for this for marketing purposes. And one of the objectives I'm doing is simplifying that and removing all the extra so that you actually understand like they're all saying the same thing, right? It's to create this standard across the industry, and that's where we get into the certification piece of this. Like, that is a very in-depth knowledge assessment so that you have something to show that you really are capable. You actually have understanding of this. You've gone through enough to explain these core concepts appropriately. Like, that is the core function of that certification, and to be able to take that and use that with your employer, with your customer, wherever the case may be, to just show you're qualified. Like, you've learned enough to try to be there. Do you have the field experience? Maybe not, but because you've gone through and you've proven that information is you understand it properly, now you can actually make some progress. Okay. So, and just like I said, everybody, I'm just doing a quick QA and just common questions I've gotten on the certification course. So we're not going to spend the whole stream on this. I'm just going to take a few minutes here in the beginning. Feel free to go ahead and get your other questions in. If you're having any issues with the stream, I apologize. I will continue to monitor it, and we'll see what happens. And if you have any other chiller or field questions, again, feel free to get those into the chat. We will get to them. I'm just covering some of the heavy questions I get very routinely about the course. Okay. Next question would be, how much or how long is the access, and how soon do I get it? Well, once you get enrolled, unless you're a company sponsored account, once you're enrolled, you get access to it immediately. Okay. From there, you're just going to go through the sign up page, which is, I guess I don't have that on cue. I can put that in the chat here. So there's a sign up page where it's got all the info and stuff. That's not what I wanted. There. So through that page, you get the info to the course. You can go in and look at all the details. I've got a ton of testimonials from just various technicians that have been through the program, and you can just read what they have to say and what their opinions are. It's straight from them. So you get access immediately, enrolling from there. If you're on a company account or they're sponsoring it, where I have to invoice, which I do have that, I can invoice for a team. I have company accounts, and I've got a whole system for that. If you're interested, for those, obviously, we've got to process the invoice, get all that stuff situated, and then I go in and set up access. So that depends on the company. There's some companies that literally I pay the same day I submit the invoice, and we can get all that situated immediately. There's some companies they take a full 2, 3, 4 weeks to cover the invoice, get everything situated, and then get you access. So that just comes back to how fast me and your company's billing department can work things out. So that's in terms of access. Now you get 12 months. You have 12 months to go through the course material and the whole program. And it's designed like that intentionally because it really helps. I'm trying to think how I want to say this. It's a way to keep this manageable and affordable, right? As much as I can. If I was to give one, I don't believe in the whole lifetime access thing because realistically, life happens, and what happens when I can no longer guarantee that long term, right? So that's one big issue I have with lifetime access. Um, and a lot of companies advertise lifetime access, but in their fine print, they define what lifetime means, and lifetime to them might mean only a few years. I just disagree with that. If I'm going to say lifetime, I genuinely mean you have permanent access, basically. And it's just not something I think is reasonable to guarantee somebody, right? So I don't go that path, but it takes a lot to have a program like this. It's very money intensive, okay? So having a year, it's plenty of time to get through this. A lot of people get through it within the first 6 months, and they spend the rest of that time going back through it or reviewing or utilizing the information. So to keep costs down, it also keeps some level of, hey, I need to get this done on your side, because there is a time restriction on it, and that time restriction, I know for me, if it wasn't for deadlines, there's a lot of things that just wouldn't get done. So one of my goals, I want to help with that process and making sure that you have the ability to get that. But I don't want to cut you short either, which is where I get into full 12 months. Like 12 months is plenty of time if you take this course seriously, where you can really go through it. So that's in terms of how long you get, how fast you get access. If you're self-sponsoring immediately, and you get 12 months in total, and you can re-enroll. Like I've got quite a few guys who have just reoccurring enrollments for themselves, to where they're just stacking them because they just want to continue using it, continue growing with it, just continue applying it for the way it was designed to do in the first place. All right, so another question that comes up is, what all is in there? So I quite literally cover everything short of absorption. Absorption chillers are the only thing I don't dive into. I have specific reasons for that. I won't bore you with the details now. But the point is, I take you through, like, starting off with just what is a chiller, getting into air cooled. These are just core concepts we understand that need to understand that apply to everything. Then we go through scroll, recip, screw, and centrifugal, and then from there, I take you into like the specifics of VRF chillers. I take you through a lot of just the basic terms that we have that we need to understand and we're going to use routinely. I show you all the different evaporator designs, what kind of numbers you should expect, how they work, how they look, so we can get into like a shell and tube deactor. And yeah, so I'm taking you through what that evaporator looks like, how it works, what kind of superheat you should expect, what kind of flow you should expect, same thing on the condenser side. Different, like here I get into condenser maintenance. It's going to be both water cooled and air cooled system maintenance, things you should expect and do and work on. We go through the types of metering valves. I do have some lessons I'm working on here, like the carrier float valve that's going to be added into this lesson soon. So there's a handful of them, that the things that weren't in the original version that I'm working on getting added. So I am routinely working on developing this course further. It currently has 23 modules, so here we get into starters, VFDs. I take you through SDRs. I take you through like an IGBT, and completely show you not only how they work, what they look like when you see them on a schematic, what they represent in the schematic, how to troubleshoot this. That's the entire purpose of what I'm trying to show you. What you're going to need to do with your meter to do that. Oil system economizers, control panels. Like there's 23 modules currently throughout the course, and a little over 200 lessons. Now I've got in the works an additional module that I'm going to be adding. I'll announce that at a later time. And then I also have uh, I've got several lessons inside of some of the existing modules of things that I want to add to the curriculum that aren't currently there. Again, what's there, you've got a complete picture. You're not going to leave not having a complete picture with what's already existing. But there's other things, there's extra nuance, there's just more to learn that wasn't part of that original curriculum I built, and I want to just make sure that stuff is covered and you have access to that information. Much of this stuff, there's just not anywhere else to get it. And one of the issues I have with, like, say, using AI for a lot of this stuff, while it has a lot of information, it has a lot of wrong information, or it doesn't know how to properly apply the information correctly. And so part of what will happen is you'll ask it about, like, what is this thing, and it can't actually describe it to you. It'll hallucinate many times, or it'll describe it in the wrong way to how we use it. It'll look at how other people, other industries use it, but that's not how we're using it. And so, and by we, I mean inside of HVAC chillers doing hydronic work. It's not how we apply that particular thing. But the AI bots don't know that. And so, like, part of my point is I want you to have a library and a reference you can come back to and actually learn. This is how we do it. This is why we do it. That's one reason why, in like in the centrifugal module, we deal with bearings a ton. I have an entire lesson dedicated to just bearings for that specific evaporators. For that purpose. Let me find it here. Yeah. Now, with this, I completely take you through just all the various types of bearings, from having ball bearings to roller bearings to the journal bearings, which you can see in here, which are a type of Babbitt. What we're using, it's a sleeve, it's an oil sleeve bearing anyway. We'd get into it. I can show you the different examples, how the bearings are being applied, what forces are acting on them, when are they used. You can see all the different examples inside of here for where you're going to see the bearings. We also review this heavily inside of the video lessons. All these are video lessons, by the way, if that wasn't clear. It's all video lessons, and then from there you can dive into the additional material throughout the lesson. So that's what in here is. It is currently 23. Will at some point in this year move to 24 lessons, or not lessons, modules, and then you've got a pretty good bank of information in each module. What's another common question I get? So we went over what's in the course, what is the course? Oh, how is it different than, say, my service or my hands-on course or class? So my service program, which is currently not open to enrollment, it is under heavy development. I have been putting a team together helping to build that out better. So if you're already enrolled in that program, you're going to be seeing a lot very soon. Anyway, those programs are built and geared in an entirely different way. I'm not explaining things to you in the same way that I am in this program. I'm not going as deep in those. So like the hands-on class that I'm doing in Houston, as an example, which you can sign up for April's class. There's still, the enrollment for April is still open. I have closed enrollment for March's class. So for that, that class is very hands-on focused. My goal is to make sure that you walk away understanding how to do a lot of different service procedures and why they need to be done and what you should expect. Now, some of that does include reviewing some of the things that are in this the certification course. So there's certain things in there where there is overlap, but most of that class is just putting the hands on and talking through actual procedures, actual processes, and then getting to do that, getting to take a EXV and test it, getting to hold a IGBT in your hand and test it, right? Those are the things that we're doing in that hands-on class, so that once you get back out in the field, you feel very comfortable doing that. I have an actual turbo core that we can tear apart, take readings on, and use that as like a base trainer to move into a lot of different directions. So that's the hands-on class. And then my service program is a series or a library of actual written instruction for how to do procedures. And it's entirely different feel to what we're doing in the certification course. So the certification course is truly built to be this is how this industry works, which is the foundation. Like, if you don't understand what's in the certification course, I can teach you all day long the practices of how to do this, how to do that, but you're never truly going to be all that successful because you don't have the right foundation. It'd be like trying to have somebody come work on a residential or an RTU that doesn't understand what saturation is. And if you don't know what saturation is and that it even exists in the first place, like, that's a lot of things. I don't know that most people don't realize how much you don't actually know in terms of chillers. It's okay. But it's the very same concept. Like, would you genuinely expect somebody who doesn't know what saturation is and doesn't know how electrons move, and how to test things with a meter, to be able to successfully troubleshoot a small commercial RTU or a residential system? Like, no, people can't do that. But we don't, like in the chiller world, parts changers don't survive. They just not in this world. People get away with that with other sectors in the industry. You're not going to get away with that here. So that's what I'm trying to do, is get you over that hump of you actually understand what this machine does, why it does it. And I take an approach of, it doesn't matter what machine you walk up to. And that's why I'm teaching you on so many brands, so many topics, like all the Train, the Carrier, the York, Daikin. I get into Dunham Bush, I get into Multistack, I get into a lot of these other brands, but I specifically focus a lot of time on the top 4 brands, which is York, Train, Carrier, and Daikin, right? Spend a lot of time on those. And that's because they are the majority of what we're going to run into, and most of what we're going to see in the industry, they all do. So yeah, I take it. I do this in a way to where it won't matter what machine you walk up to. You will walk up, you'll see, okay, the evaporator is designed like this, that makes it a falling film. I see my condenser looks like that. Okay, it's a standard shell and tube condenser. I see that I have a metering valve here and it ties in on top. Okay, so got that. That's going to be a variable orifice, for example. This is a single stage compressor, so I don't have an economizer. Right, so you can just roll through this really quickly and get a lot of your core data, even though you've never seen this machine a day in your life. You can very rapidly assess that machine's intended purpose and what kind of readings you should expect it to do, just based off of how it's designed. And each of those have very standard ways of operating, right? What we expect a falling film evaporator to do doesn't change from one brand to the other. All the brands do it the same way. So it's just a matter of understanding how the falling film evaporator works, and then you understand that evaporator despite what you walk up to. Same thing with flooded, same thing with a shell and tube DX. So, like, this is why I'm taking the approach that I do. It's the whole point of the concept. And that's why this course is different than some of the other trainings that you do see that I offer. Okay, we've spent enough time on this. There are other questions that do tend to come up, but I think those are some of the core, like, main ones that we'll focus on. And we'll roll into some of our normal programming from here. How's everybody doing? Hope you're doing well. Hopefully you're not asleep and you're still around. If not, I'll just talk into the void for a minute. That's okay too. Um, we can get our next question spooled up here. Hope you've all had my weekend, I'll say, has not been all that fun. It's been it was a lot. We had to drain the kitchen drain line back up, had to get under the house, snake it out, got into a wreck. It's all kinds of not fun. Had a good time with the family. I wasn't being moody and a jerk. Had a good time with the family, but granted, I was being moody and being a jerk quite a lot, so not my best showing. Alright. Can you go over your method for pulling gas on air-cooled chillers? Do you ever pull, or do you ever use the pull-pull method, or do you just recover normally with pump-on? It's a very, very important question to go over properly. We briefly talked about this in the last stream, and I want to really make sure we cover it in proper detail here today. Okay, so let's first kind of define some of the methods we have. So we have a standard recovery. Okay, let's just get on the same page here with our definitions. So we have standard, and we have push-pull, and then we have pull-pull. Okay, so the standard is just what you would always expect, right? So we're coming straight out of the machine into our recovery machine. All right, so let's say this is our chiller. Call this a recovery machine, and then we push that into our cylinder or our tank. So we'll just call that T for tank. Standard recovery. Now, with a push-pull or pull-pull, what these are is a more rapid way of getting our liquid refrigerant out of the machine very quickly, because that's where most of your time is going to be killed. If you're doing a standard recovery, you're trying to boil out the entire refrigerant charge on the system, which takes absolutely forever, but sadly, especially on a lot of air-cooled lines, is necessary. So push-pull and pull-pull are only effective when you actually have the liquid refrigerant consolidated into a central place inside of the system, which is going to depend on the evaporator, and I'll explain that in just a second. So covering push-pull first, basically, we have our chiller. We come out of the chiller into our first tank, or into our tank, out of that into our recovery machine, and then back into the chiller. All right, so we're flowing this way. So what's happening here, this is the first stage of the process. Both of these are kind of a two-stage process. We're pulling the liquid off out of the bottom of the chiller into a tank that is catching that liquid, and we're pulling vapor off of the recovery cylinder and pushing that vapor back into the chiller. It creates a push-pull cycle. We're pushing and pulling at the same time. It's the general theory, and we're collecting the liquid refrigerant here. Eventually, once all the liquid is out, we switch back over to a standard recovery and pull all the vapor. Simple as that. A pull-pull is a slightly modified version where we come out of the chiller. We have our liquid capture tank just the same, okay? We pull vapor off of that just the same. But then we go into a vapor capture tank instead of back into the machine. Both of these are extremely effective methods. I think they both have their place. I've used both for a lot of years. I learned this from Rapid Recovery, which the founders of that now own FM Hero. So that when I first saw this method, that's where I first started using it. My go-to is push pull, and I use pull pull just depending on the circumstances. Like it really really depends. Um, Both work great when done correctly, and both work terribly when done incorrectly. Just saying. So, okay, now we understand what we're discussing, and when we talk about, do you ever use pull-pull method, and we're discussing an air-cooled chiller, we're clear on what methods we're describing here. So we have standard, push, and then pull-pull. All right. Now, I said that the evaporator matters a lot. So let's quickly just, there's four main evaporators we should expect to see. All right. So we've got braze plate, BP. We have the DX, ST, shell and tube. Then we have a flooded, which is also a shell and tube. Then we have a falling film. I'm just going to say FF, falling film. Okay, both of these, the refrigerant is on the outside of the tubes. So it's on the shell side. So ref on shell side. These, well, okay, not braze plate. The DX shell and tube, ref is in tubes. And then braze plate's braze plate. Okay, I don't think I need to over explain that. So that's your core difference here. Now, both of these, many of those systems will end up doing a pump down. Someone pause real quick. He said mic checks. Are we still having issues for folks with the mic? My mic says it's supposed to be working. Let me just do a quick touch base before I keep going here. Can everybody hear or see me appropriately? I'm sorry for the technical issues today. As far as my computer is concerned, I'm working better than most days, actually. Like, I'm actually very stable today, which is not typically been true. Maybe that's the problem. Maybe I should be unstable, and then it'll be better. Because most of the streams, I'm very unstable, and then I don't. It doesn't seem like people have issues. Can you hear me correctly? Unlistenable. Man, what is going on? I got that turned off. We look good here. No problem with video. I'm really wondering if it's the YouTube stream side. Might be your mic or mic cable. See you fine. Okay, so you can see me fine, but we're having a mic. Okay. If you can't hear me, then we need to fix this. Okay. So it's there. Let's do some quick troubleshooting. Let me pull up my stuff here. Yeah, that's right. Okay. Yeah, let me work on this for just a second. Switch. Mike. Yeah, that's not. Here, let's do it. Alright, we're going to use this as a quick test. So this is a different microphone, not a good quality one. Can you hear this microphone by chance? Because I'm trying to determine, is it this mic or is it something with the computer and the stream? Okay, so now you can hear me. So I'm going to switch back to the other mic. Okay, so now we're back on to the original mic. How about now? Is this mic working better? Did I just need to do the whole turn off, turn on again? Are we any better? Yay, nay, yay, nay. Doesn't seem like it. Looking good there. Looking good there. Yeah, bad now. Okay. I'm gonna let's see. Hang on. Okay, I'm gonna reboot this mic real quick. I appreciate the patience. Let's just see what happens. Okay, it's rebooted. I'm gonna switch back over. All right, how about now? Are we working better now? Yay, technology. Anything? No? Is it better now? Mic test, mic test. I apologize. I apologize for the technical issues, fearless. I'm trying. You know, why wouldn't a rough weekend just turn into a rough stream, you know? Let's just keep. Okay, so it's working now. No, bad again. Okay, alright. I've got more tests I can do. 1 second. Okay, no, not that. Just give me 1 second. I'm gonna figure this out. I'm locked in now. I ain't giving up. That's right. How about that? Is that any better? So I turned off one of the settings. Is that any better at all? Yeah, I'll end up. Okay, this is gonna be my final attempt. I did the whole unplug and replug. If this doesn't work, I'm just gonna go with the other mic. Final chance. Are we working? Final no. Doesn't seem like it. Okay. All right. So we're just gonna roll. Oh, we're gonna roll with this mic. Yep. Okay. Let's see. Yep. Okay. Obviously lesser quality, but I guess not. Maybe not now. Um, we do have a lot of static on this one. Let me try to clean that static up real quick. Okay. That should clean up some of the static. It may sound kind of weird with the filter on it. It's not a perfect filter, but some of the background noise should be clearer. Okay, not that bad. All right. Let's see. Mic check, mic check. Okay, yeah, we look good up there. So this is one of the built-ins to one of the cameras I use. That's so weird. Oh, I see. How many technical issues can we create? It's fine. Yeah. There we go. It's listenable. It's better than incoherent. Okay. So should I take that to mean we just start over? Should I just redo this whole segment from the top from the beginning? I don't mind. I can start over if that's better. I don't want to. Sounds like I should. Y'all tell me, start over or just keep going from where I'm at? So I was just getting into why the evaporator matters. The original question, just in case, go over methods for pulling gas out of air cooleds. Yeah, start over. Okay, let's just do that. We're going to start over. Take two. Yeah, I tried to. Well, no, you did, man. You did. You tried to warn me. I was hoping it improved. I was hoping it improved or it would improve with time. Obviously, I have absolutely no idea what happened. It probably is the cable. I don't know. I'll figure it out later. Um, yeah, I appreciate everybody though, and I appreciate the patience. Because why not? Right? Why not? Okay, let's get into it. Let's start from just the very beginning. Can you go over your method for pulling gas on air-cooled chillers? Do you ever use the pull-pull method, or do you just recover normally with pumps on? Okay, so first we need to clarify a few definitions here. One of them I want to clarify is what type of method are we discussing trying to use here? So there's three primary methods I'm going to bring up today. We've got the standard, we've got push-pull, and then we have pull-pull. All right, so standard recovery is exactly what you would think it would be. All right, so we have our chiller, we come out of chiller into recovery machine, out of recovery machine into our recovery cylinder. I'm just going to refer to it as tank, okay? Basic process. All right. Push-pull, we're referencing a slightly more advanced version. I say slightly. I mean, so this is a more advanced practice in general. It's important that we have access to liquid, to the liquid in the machine, which is where the evaporator becomes really important. We'll get into that in just a minute. So for the chiller, we're going to come out of the bottom of the chiller where we can get the liquid refrigerant. And that's going to come into a capture tank or a recovery tank. From there, so it's going to come into the liquid port. We're going to come out of that into out of the vapor port into our recovery machine. And the recovery machine is going to push that vapor back into the chiller, and it creates this whole loop or cycle. Okay, this is a push-pull. Both of these are kind of a two-phase process. So phase one is we're getting all the liquid like this out. Phase two would be going back over to a standard. So the standard recovery would then remove all of the vapor. And the whole point of why this matters is when we're trying to do a recovery and we can't get all the liquid out, boiling that liquid refrigerant out of the system, especially when we're talking the scale of some of these systems, takes a huge amount of time. Like it's a huge amount of time. Because it's a very inefficient process compared to if we can literally just remove all the liquid out or as much as we can possibly get access to, and then pull only the vapor off once all the liquid is out. We're not trying to boil all that liquid out of there. We significantly improve the efficiency of our recovery. That's the whole point of why we even care about this in the first place. So pull, which I get from I'm blanking on the guy's name offhand. I apologize to him. Really cool dude. He was one of the co-founders to Rapid Recovery, and that's now owned by A-Gas, and they went out and started FM Hero. So I'd highly recommend Go check some of those guys out. They did a whole thing with the Chiller Guys Hub where they did a live stream discussing the pull method. But that's where I learned this years ago working with Rapid Recovery. I mean, long time ago. I don't remember exactly when that was, but either way, it's a different version of the push pull. So we're still going to have our chiller. We're still going to pull liquid out the bottom of the chiller into a liquid capture tank. But then we're going to go out of the vapor port into our recovery machine, and then out of the recovery machine into a vapor capture tank. And that's the whole chain of the pull process. So we go from chiller to liquid capture, recovery machine to then vapor capture. And instead, it's just not cycling through. To be frank, both of these methods are extremely effective. I think they both have their place. My go-to, just because it's what I learned first, that's what I've done for the longest, is using a push-pull method. This is kind of my go-to. I use this as kind of a backup option if I feel like I need to, or if I don't feel push-pull is good for that particular job, or if I'm just feeling spicy and I want to change things up that day, I'll go pull for the fun of it sometimes. When done correctly, either of these are very, very comparable. And when done incorrectly, they're just not really going to do much for you, okay? And it's really, really important to understand when and how to apply these. And again, the goal, get the liquid refrigerant out, then we can move into our vapor recovery via a standard recovery like we do on any RTU, any system. Now, I said the evaporator matters here. Let me explain why. So let's cover the primary evaps. So we have a braze plate, we have a DX, direct expansion, shell and tube, ST. Then we have a flooded. Then we have a falling film, shell and tube. Both of these are shell and tubes. These two here, the refrigerant is outside tubes. So it's on the shell side. A DX shell and tube, the refrigerant is inside tubes. And so the water is on the shell side. And then we all know what a braze plate is, or should, ideally. So these two here both go through a pump down cycle. Okay, or typically most machines that use these will do a pump down. What that means is that the refrigerant is not being stacked in the evaporator, but that is not true for these. These actually hold the majority of the charge in the evaporator, and at shutdown, they stack a lot of that charge into the evaporator. Now, there are some machines out there that will that have the ability to do a pump down on these two styles. Like, you can do that, but that's the exception. Most don't. And when they shut off, they automatically let that refrigerant move into the evaporator, or at least the vast majority of it. So what's great about these is if we have access to that liquid refrigerant that's collected in these evaporators, with the exception of YVAA, of an example. Okay, we can get into those details separately. If we can get to the liquid refrigerant here, then doing the push-pull or pull-pull method works, because then we can directly get all of that liquid refrigerant out of there very rapidly. When we start dealing with these two, which is what the majority of air-cooled machines are. Now, there's a lot of machines that do use these, okay? So I'll give some examples that use a flooded. So we could go with a YV, that's not a V, a YVAA, okay? A RTAC, a ACR, RTAF, the 30GX, 30XV by Carrier. The was it AWS AGZ the AG no the AGZ. I'm blanking on the Daikin ones now. Anyway, Daikin has a couple of flooded. Pretty sure they have a couple of flooded air cooled. Anyway, these are some examples that would use either flooded or falling film. So technically, YVAA, falling film, RTAC, falling film. 30GX is a flooded. 30XV is a flooded. Anyway, in terms of how to tell the difference between all these, like that is exactly what I'm teaching in my certification course, by the way. So if you really want to get into all the details and understand, like you walk up and, oh, okay, I know exactly which type of evaporator I have. That's what that course is built for. So moving on from that, I know that this particular question actually came from somebody who was looking to do a recovery on a CGAM, a CGAM by Train, which is an air-cooled scroll machine. So they do not have this. Like if when you're dealing with the vast majority of air-cooled, you're dealing with one of these two. What that means is that it is not worth the time or effort to try to do a push-pull or a pull-pull on those systems, because even if they do a pump down, the liquid refrigerant is not in a place where it is truly consolidated and easy to recover from. Like just purely getting that liquid refrigerant out. And you still end up having a lot of liquid that has to be boiled out. And I'll give some examples of this. So like falling film and flooded, okay? So we'll just say FFF, okay, flooded falling film. Pick one. They'll have a service port down here at the bottom of the evaporator. And that's where we can draw that liquid out from. But on these other machines, like we can use a CGAM as an example. Coming in, so those have a brace plate evaporator. And right here's your metering device, and there is a liquid service right here, and it is kind of down at a lower point, right? So it's coming down from the condenser. So that's our liquid line flowing in. The problem is it's right on the top of the pipe. Like when we start dealing with all of that stacking on top of the pipe, that's when we really start getting into trouble. Because if you think about it, when our service valve is up here, okay, just imagine that's a valve. There's your threads, whatever. Once that liquid refrigerant gets down past a certain point, we're only pulling vapor, and there can still be a lot of liquid stuck in that pipe, but not actually making it out of the port. And it's not like the port's on the bottom. If the port was on the bottom, then a stuff like that would make a lot more sense, which is why these are so much more effective. But when we start dealing with brace plate or a DX shell and tube, we don't have that same access and ability. Because even like, say, a YCIV by York, they have the same setup. There's a 3/4 inch, or I'm sorry, 3/8. There's a 3/8 service port on the two-phase line, leaving the drain valve coming into the evaporator. It's okay if you don't know what those terms mean, or that's okay. Point is, between the metering device and the evaporator, there's a 3/8 service port. The problem is two things. One, they put it on top of the pipe. Two, it's on an angled up. So many of those machines, the two-phase line comes down and around, and then angles up into the evaporator. It is on the upper angle of that line coming through. So, not to mention it's a pump down machine to begin with. So that whole evaporator on those are empty if they pump down correctly in the first place, and they haven't migrated. So, long story short, in this scenario, it's not worth your time. Could you get a little bit of liquid out? Sure. And I encourage you, if you haven't done this, do some experimenting. Try to implement a push-pull or a pull-pull method on a circuit like this. Just try. you'll find that you'll have some success. You will get some of the liquid, and maybe that's worth it to you. But in my opinion, and this is where on these smaller machines, because these are small machines that we're discussing here, when we're dealing, because all these circuits are going to be typically less than 100 pounds of charge, typically. Some of okay, I take that back. Some of these may scale into like 120, 150 pounds per circuit, but the majority of them are going to be less than 100 pounds for what we're describing here. And when we start getting into these other styles, that's when we start having higher refrigerant volumes. We also have anyway, details. Try. Just experiment. See what happens. Yeah, you might waste a little bit of time. I like to use recovery machines that are liquid capable. That's why I like the NRDC4M. I can write that down. It's a Navic pump. I am absolutely in love with this pump, man. So the NRDC4M. You can get this at TrueTech Tools, by the way. Like I have I'm a partner with TrueTech. So if you ever wanted to order tools through them, just use the code HVAC time. You can get some discounts there. Point is, this pump is incredible at pumping liquid refrigerant. It's designed to do so. They're not like a normal reciprocating compressor. These are actually designed that you can move liquid refrigerant through them. Because of that, to me, I like to use that pump on these types of systems because what little bit of liquid I can get access to, I can just send it straight through the recovery machine. I don't care, but I'm not having to reconfigure then to get set back up for a standard recovery after already setting up for, say, a pull or something else. I'll just let the machine grab whatever liquid is there, and then you're just going to have to boil off the rest. It just is what it is. So these machines are not good candidates for a push-pull or a pull-pull style recovery. And so I can give a list of some of them offhand that I can think of. So that would be let's see, a CGAM would be one, obviously. A YLAA would be another. That's your York brace plate. I think they actually did make the early versions of these, I think, had a DX shell and tube, but then they switched to, I think they switched to brace plates. Let's see, a 30 RA, 30 RB, and then you have a 30 RAP, very unfortunate naming their carrier. Let's see. Like I said, these are all machines that I would just go straight into a standard recovery with. So YCIV would be one, RTAA. Oops. AA, there we go. If y'all have any recommendations, like what are some machines we can make as a list of? I wouldn't even bother with trying to do a liquid here. Anyway, I could spend a lot of time on this. Point is, these machines either have a brace plate or a DX shell and tube. They're not worth your time trying to use those advanced practices. It's better to take the time to just hook up standard, have a good standard recovery setup, larger hoses, make sure you're using a subcooler, like do all the more advanced practices, and then you're going to do really, really well trying to get that refrigerant back out of there without any issues. And you're not going to waste any time. I've experimented heavily with this over the years, really just trying to perfect my own practice. And these are the conclusions that I've come to through using all kinds of different recovery machine setups, hoses, practicing the different recoveries, like really just trying to vet this stuff out. So that's my recommendation. Does the approach value change? Yeah, so we'll get into the approach question in just a second. Do we have any follow-up questions to this recovery practices or anything like that? And then I will address evaporator approach momentarily. I want to make sure we conclude this topic first. And like I said, if there's any questions on this, feel free to throw them in real quick.
All right. We still doing good on the mic. Everybody can hear. Everybody can see. We're good on the stream feed itself. Which before I continue moving on. What is advanced in pull method? So are you saying what is advanced about it, or what is the method? I guess I can answer it both ways. Um, I say it's advanced because it's a higher level of doing a recovery um, than just doing a standard, right? So we come up in trade school or whatever you learn the industry through. We just learn the standard process out of the machine into recovery into cylinder, right? Very basic process, nothing else in between. And so as you step into larger tonnages, larger machines, we need to improve our practices to match the more advanced machines. Well, we have more advanced practices too. I'll throw using a cold strap in there as an example of a more advanced practice for evacuation and dehumidification that you're not going to learn about in school most of the time, and you're just not going to see on smaller equipment, but you will see it when we start getting into what we work on, especially being the fact that we work with hydronic evaporators and sometimes condensers if it's water cooled. Um, so again, that's why it's a more advanced practice. It is it's taking a higher level to what higher level to it. I mean, what are the advantages of using? Oh, I see. What are the advantages of push pull? So, uh, or not, you said pull. What are the advantages of pull are you're capturing, so you're still capturing the liquid. All right, so we can get into that. Actually, we'll come back to the approach. Let's just keep on this train of thought. Um, Let me get this question. This will be just for everybody following up later in the stream. You work. Here we go. Okay. So what are the advantages of using push pull or pull? I'm sorry. What are the advantages of using the pull method? I could talk today. So you're still capturing the liquid refrigerant. All right. So if this is our chiller, we're pulling out of a liquid recovery port on the evaporator. We're still getting into the we're coming into the liquid line here on this tank, this recovery cylinder. We're coming out of our vapor into the recovery machine. And then we come out of the recovery machine into a vapor tank. So this is only going to capture the vapor coming off of the recovery machine, which is coming off of this tank. So part of what's happening here, this recovery machine is drawing this tank down, or this recovery cylinder down on its pressure. As this pressure is reduced from the vapor port, it drops the pressure lower than the chiller. The chiller naturally feeds liquid refrigerant into this tank, and then out of that into the vapor out into the recovery machine, and then into our vapor capture tank. Okay, so we're still getting all of the liquid out without having to boil that liquid out. So that's the main goal of what we're trying to do here. Is we don't want to have to boil out the liquid refrigerant. And doing this, there are some key benefits. If we know that we're not running the risk of recycling, like if these tanks, for example, weren't properly clean, if we do a push pull, we do run the risk of pushing whatever trash may be in the tanks into the chiller. That is a risk. If we have leaks or contamination in our recovery machine or hoses, things like that, doing a push pull, we do risk putting those contaminants into the machine. It just is what it is. And the benefit to pool is we're not running that risk of those contaminants. Or another example could be if we do, say, like your hoses, or you've got a fitting or somewhere leaking on your system, and you're doing a low pressure recovery, especially, and you start drawing in non-condensables, well, then you do run the risk of actually pushing non-condensables into the chiller, which are not going to come back out during the vapor recovery phase. Those are going to get stuck in there while you're trying to get the vapor refrigerant out. So that is where there is a strong argument for the pull method over, let's say, a push pull method. And there is debate on how effective push pull really is on increasing throughput compared to pull. So one of the keys to pull that makes it that makes it work is we have to use a subcooler on the vapor side. So as we discharge out of and some of these can be built into the machine. The NRDC 4M recovery machine that I mentioned has a built-in, and it's a phenomenal one, subcooler. It has one built in. And these are the machines I'm actually teaching with in my hands-on class that I do in Houston. I have a set of NRDC 4Ms that we hook up. I show you the subcooler process. I show you what all this looks like. So it's just part of that class. But you need to have a subcooler so that you can de-superheat the refrigerant for this tank. Otherwise, as this tank builds pressure, you'll kill your entire process, and you're going to have issues getting this to work effectively. So it's really, really important that a subcooler be used on that vapor tank, which is not true with push-pull. So when we're doing a push-pull, because we're just recycling, so like for me, one reason I like push-pull better is because we're keeping our differential across our recovery machine lower. So lower differential pressure across the machine, inlet and outlets, or a lower compression ratio, we have a higher throughput. So the total CFM moving through the recovery machine stays higher because of just because we're recirculating. We also do hold the machine's pressure a little bit higher. So with this method, that saturation temperature inside the machine does drop more with this compared to push-pull. Now, some of the claims with push-pull is, okay, well, we're not increasing the machine's pressure with a push-pull. That's not what we're doing, even though that is some of the arguments that I've heard. No, what we're trying to do is we're trying to keep a stable pressure that is higher than if we did just a straight pull like this was. So you will see lower saturation temperatures with this method in the machine than you would with push-pull, and you don't need the subcooler on the discharge side for capturing that vapor refrigerant. So ultimately, that's the high levels. We don't risk adding contaminants to the chiller by recycling. We also get to capture all of our liquid refrigerant. And if you use a subcooler on the discharge side going into your vapor tank, it is an extremely fast, effective method. So those are your primary advantages of why pull is worth your time. And I am saying pull, just so we're clear. Okay, this is a pull method. And I can 100% vouch, works really well. All right. Let's get into the approach question. All right. Is approach value change in different evaporators? I mean, flooded to DX to braze plate. Yes, they change significantly. Let me show you. Let's look at what I mean. Okay. So let's just quickly talk about just what the evaporators are that we're discussing. So with a braze plate, we literally have a heat exchanger. Okay, and where there's these internal plates that separate it. So what's coming in over here mixes on one side, come in and out. So let's say it's going to blend on this side, and this side. And then on this other side, we could say, let's say, refrigerant coming in and out. So this would be your water, refrigerant is going to be on these other chambers. All right, pretty cool setup. There's seals isolated internally here that protect these circuits from intermixing. So the water and refrigerant don't blend. But we can still exchange heat through these plates that have corrugation to them, so that there's more surface area, and it also creates more turbulence in there for heat exchange. All right. Now for a DX shell and tube, we're actually going to have water coming into the shell side. Okay, so water in, water out, in, out, and refrigerant is going to be coming in through the end bell. So there should be a suction line in. This would be suction line in. This would be refrigerant out, or suction line out, refrigerant in. And this is a automatic. So this is your end caps on either side. You're looking at a side profile of the evaporator. And then we have our falling film or flooded. So I'll just kind of combine these into one, where the water, I go much deeper into this in my certification course, but the water is on the end bell side, and then the refrigerant is coming in to here with our suction line coming out the top. Okay, this would be our suction, this would be our refrigerant in. All right, so each of these have their own purpose of what they're trying to do. Okay, my understanding, brace plate, they're smaller, they're more compact, and they're a cheaper device to my understanding. And when we get into like a DX shell and tube, these are difficult to scale, especially within the format of, say, like an air-cooled chiller or something. Where these, the DX shell and tube, scale much better. Let me actually label these. So we have a brace plate, direct expansion shell and tube, and then we have a flooded falling film. All right, so other than why we have differences, like these are the most efficient. We're going to get the most effectiveness out of our refrigerant by using these, and that's part of what we're measuring with approach. So approach, refrigerant approach, or evaporator approach, we'll say it that way. Approach is, if I could spell today, equals, let's see, the leaving water temp from the evaporator minus evap sat. By sat, I mean saturation, evaporator saturation. Subtract these two from each other, you get approach. We're measuring how effective, how well we're transferring heat from one to the other, from the water side to the refrigerant specifically. This can be flipped and inverted for the condenser side. We can say it, but it's just for simplicity today. How well are we moving from water, heat from water, into the refrigerant to do otherwise with? Now, these two are less efficient. We know we can tell that because they run higher approach values. They just don't do as well, but they require less refrigerant. They're cheaper in that way, as you don't have to put as much refrigerant into the machine. And they're, from my understanding, is they're cheaper to manufacture compared to these styles here. They also don't have some of the same oil return issues that flooded and falling film have. So with these, you have to have oil mitigation where we're taking the oil back out of the evaporator. Like there's more to that process that these don't have to worry about. As long as you have enough velocity, another way to say that is differential pressure across your circuit, you can always get that oil back through that evaporator back to the compressors. That is not true with these. The falling film and flooded, that oil will get stuck in there, and we have to have some kind of oil recovery circuit in order to manage that, which adds a lot of cost and a lot of complexity to any machine. So it also impacts reliability to a degree. Like this is a oil getting migrating to the evaporator is a common call for machines that have these types of evaporators. All right, so the question is approach. Do they change? Yes. I will say this because factory guys give me grief about this all the time. Refer to your design data. Every machine is unique. They're all designed to do specific things. Let's see, what other lines am I supposed to say? Get it from your local service shop of whatever that model and serial is and follow that design data. Okay, now that that's out the way, most of these evaporators for braze plate and DX shell and tube are going to be running a 8 to 10 degree Fahrenheit approach at full load. Okay, that is a critical point here. This is at full load. Flooded and falling film are going to be usually running a 3 to 4 degree Fahrenheit at full load. I want to really hone in on that full load. Okay, what that means is as the machine unloads or derates itself and whether it turns compressors off, unloads them via slide valves, speed slows down, however the heck it is that machine's doing it, you should expect this to drop. That would also mean that your differential across here, so if their design differential is 10 degrees from entering to leaving water temperature, so let's say we're going for 45 degree leaving, that's our target. We have 55 coming in. If it's designed for a 10 degree delta, that would be a fully, with good GPM, that would be a full load. I know there's a lot of technicalities here. I'm sorry. I'm trying to high level this. Again, if you really want a proper explanation where I break this down, the certification program is your place for that. Okay. So good GPM at design, this is what you would expect. As we unload, these numbers should drop. So if I have a compressor running at 50% capacity, then I would expect this number here to drop roughly accordingly. So that may mean I only run 5 or 6 degrees at minimal capacity. This one may only run 1 or 2 degrees, if that. So like these will significantly reduce as the machine unloads, and there's no like direct just blueprint there. But this is how the approach will change and be affected. And if for any reason you do see any tube-in-tube machines, maybe you're working on some small process chillers, those will also be an 8 to 10 typically design approach value. 10 being the most standard for these. Like the vast majority of these will be about 10 degrees at full load. Now keep that in mind from a service perspective. If you are seeing full load approach values at partial load, there's a problem. Investigate that. We shouldn't have that. So those are things you can look for, and that is where experience really comes in, because if you don't know that, then you could be heavily unloaded or derated, but yet still running high approach value, but it's still within specification. Okay, don't let that trip you up at some point. Okay, understand that these numbers all work together and they fluctuate together. As the machine derates, these numbers should also follow that trend, and they do the same thing as they come back up. Same thing with like the motor current on a compressor. Let's say a screw compressor follows the compressor slide valve or speed. Okay, so as the slide valve loads the machine. Okay, if you don't know what that looks like, do I have one sitting right here on my desk? I absolutely do. So this is what your slide valve is going to look like inside of there, or a version of one. Okay, so as this is sliding into a loaded position, the motor current is going to follow that and increase because the compressor is doing more work. All right, as we unload the slide valve, compressor does less work, motor current drops. All right, you've got the basic concept. So as we increase load on the evaporator, approach temperature increases with it. We decrease load, approach temperature should decrease with it. Same exact correlation here. It's the exact same concept, just applied in a different way. So we have to think about this stuff, and this is part of what makes data analysis so tricky as a service technician, because we have to think about all these various relationships and how everything is tracking and moving together. This is why what we do is very complicated. Anyway, that's the high level answer to is approach value change in different evaporators between flooded DX and brace plate. That's a very high level review of what that means and why it functions that way. Great question. How you doing, Sterling? I see you there, by the way, bud. Sterling, you missed the whole saga. We had a whole troubleshoot and everything going. Like, you missed it all. I had a question about the evaps and approach. All right. How does approach change with loading up or down the compressor? Does approach now? Oh, okay. All right. Well, you've answered a lot. Okay. So no, I didn't see your comment there at first, but I see we're on the right track here. See, compressor, does approach change when you have one circuit on or two circuits on? So yes, the approach value. So let's say you go from if you have a two circuit machine and the only one circuit is running, the second circuit turns on and now you've got both circuits together. They do affect each other because both circuits are now sharing that heat, and the approach value will shift a little bit. You will see a little bit of a shift in the approach, and I can give an example of this. But let me finish your question. But the technicality of why does approach decrease when load decreases? Amazing question. Yes, amazing question. Good job, Sterling. All right, let me see. We're going to take this part of that question. Let me build this out here for just a second. That way everybody has a reference. And then we'll take this, and then Y. Yeah, for once, I'm asking a good one. Yeah, not a controversial. You're not trying to stir the pot this time. I appreciate that. Let's see. Does approach change when you have one circuit on or two circuits on? Why does approach decrease when load is decreased? Okay, so we've got kind of a two-phase explanation here that we're going to get into. So in terms of it changing between circuits, so let's just kind of work through that real quick. All right, so let's say this is our evaporator, and we're gonna deal with I'm just gonna use a DX shell and tube as our example. This is going to be true regardless. So we're looking at a top view of the evaporator. So top view. All right, so that means our circuit is here. Okay, we have our comp 1 and comp 2. Close enough. All right. So when this comes through, comes out, yada. If there's baffles in here that intermix the water and do all kinds of stuff. All right. As one turns on, so this one is on, this one is off, we will see a, let's see, approach is going to be lower with just one compressor on, waiting for the second one to turn on. And that's because there's all the heat in here is being concentrated to just that one compressor. And this gets into kind of the second phase of the question of why does approach decrease as load decreases? So we'll get to that. What you'll see is, okay, so this compressor will stage up. Now, as this compressor, let's say it stages up first to maximum on its own, and then the other compressor comes in to join it, what you'll see is this compressor will start off with a really low approach, and then as it runs up, the approach will increase, but depending on the circumstances, it may not hit maximum approach, right? So we may not actually get to that full 10 degrees, even though the compressor is running at its max rate. It could, but it may not. And that's when compressor 2 gets called in, and that's just saying these didn't turn on together simultaneously. Then when the second one turns on, now both of these are having to share that evaporator. And that means that all the heat that is in that evaporator is having to be split and shared between the two circuits. And this ultimately creates a higher approach value on each circuit. So both circuits, and specifically compressor 1, we had an example of its approach by itself, but now we've got circuit 2 involved, and now it starts staging in the exact same staging points that it had just a moment ago with by itself. You're going to see a higher approach value in total. All right. A way to look at this is the exact same concept as an inter. It's not interstage. It's not interwoven. There's a specific type of evaporator where there's two circuits that get interweaved, and they're not staggered or stepped. It's inter something. It's not interwoven. I don't think it's interstaged. I forget this specific term. Anyway, so we can take this to an RTU example. All right. So in an RTU, just make some room here. We have our evaporator coil. All right, and both circuits are interlaced into this coil around each other. All right, so our metering device would be feeding in here, it's going through its tubes, coming out suction line, and we've got two circuits in here total feeding into this coil. Now, so we'll say 1, this is 2. So when it's just circuit 1 running, trying to process this coil, let's say we're trying to achieve a supply air set point, so an SAT, supply air temperature set point, you will see that your evaporator saturation runs higher. Okay, now even if you're hitting set point, let's just say you had a low load on this RTU and you were hitting set point, because we only have one circuit on this interlaced, oh, maybe that's the term. Okay, interlaced. I think that's the right term. On this interlaced coil, it just comes to you. Anyway, because only one circuit is activated, the entire heat load of that coil is being taken in by one. What that means is there is a lot of heat for just the one circuit. So you're going to see higher saturation values, even though we may be achieving our supply air temperature set point in a low load condition, for example, or a derated condition. But then we need to get say the load increases, we're losing supply air temperature set point. Now we need to bring in the other circuit to pull more heat from the coil. Well, now both circuits have to share that heat, and they're interlaced with each other. And so, like when they're interlaced, like their tubes are literally, not overlapping, but they're all tied into the same fin assembly. So you're going to see the saturation suddenly just drop. Not plummet, not in a negative way, but it's going to go to what basically you would consider normal. So let's say you're running a high 40s to pushing 50 degrees of saturation when this circuit 1 is by itself. But then circuit 2 comes in and kicks in to help circuit 1 on this coil, and all of a sudden both are running at, say, the right at 40 to the mid 40s, or I'm sorry, the low 40s in saturation, and now we're achieving that supply air set point we're trying to get to. And again, this saturation dropped because now it's sharing that heat load with another circuit, and it's not got the entire heat load to itself. This gets into the kind of the second phase of this question, is why does approach increase or decrease with load? Keep in mind, we use a different version of approach when we think of air over coils or DX coils, direct expansion like this with an evaporator, because we think of it as, okay, what is my return air to saturation, and then what is my saturation to supply air? But most of the time I'm thinking, what is my return air to my saturation temperature? That's what I spend the most time analyzing for a DX evaporator, air over evaporator. But in the water hydronic evaporator, instead of an air over, we refer to it as a approach value. Now, getting into why these are, getting into why it matters, it comes back to rate of heat exchange. Okay, so as load is reduced, so we have to remove less total heat, and we can unload the compressor. We're pulling less refrigerant from, or we're pulling less hard on the evaporator, which means we move less CFM. Okay, so let's just draw a circuit. I think this will help visualize. We'll use an example here. We'll get our little compressor buddy. So let's just say this is our suction coming out of the evap. Okay, and then we've got our metering device and a condenser and yada yada. Okay, we all know a basic circuit cycle. All right. Let's get our water. As this compressor unloads, we're moving less CFM through the evaporator. A natural result of that is we're going to increase saturation a bit. Actually, we're going to increase in comparison to where we were, but it might actually stay fairly stable. So if we had, man, I'm trying to be careful with how I explain it so I don't just add more confusion just by saying a bunch of random words that don't actually connect together correctly. So I'm really trying to filter how I'm saying this so that it is easy to receive. Let me take a step back. Let me just keep this as simple as I can, because this can turn to spaghetti real fast. We have less refrigerant moving through the evaporator. Because of that, we're not pulling down on the saturation temperature as hard. Now, we do end up feeding less refrigerant as well. So there is a balancing act that happens here, but ultimately, we're not drawing down on the evaporator as hard. At the same time, we do have less heat being moved through this evaporator because we're at a unloaded state. So let's say our design was 10 degrees, okay, so design was 10 degrees Fahrenheit, but let's say we're only moving 6 degrees Fahrenheit as our actual TD across through this evaporator. So now we have less total heat that we need to remove in order to achieve set point. All right? Because of that, our approach is representing. Our approach represents how much or how efficiently we are moving heat from one to the other, and it is heavily dependent upon how much heat we need to move in the first place. Okay, so as we know, the greater the distance between two objects, okay, I'm sorry, let me say that correctly. With temperature, the greater the temperature differential between two things, the faster the heat moves to try to equalize that heat. Okay, so we're getting into refrigeration 101. So the more difference we have, the faster we can move because we're trying to come to equilibrium. We're trying to nature wants a balance between the two temperatures. So as we need to remove less heat, we need to add less heat to the refrigerant. This process allows us to slow down that rate of exchange. We don't need to give the heat as fast, or as we don't need to give as much volume of heat from the water to the refrigerant, because we can reduce the volume of heat, the total BTUs needed. We can reduce how much temperature difference we have between saturation and the water. And because we can reduce that temperature difference, that is reducing approach. So the approach is just representing how much difference we have and is needed to achieve the BTUs we're asking of it. That's why at full load, we have a 10 degree design approach for this evaporator. But as the evaporator unloads, there's less BTUs going through it. The circuit is having to manage a lower capacity. It also means that we don't need as much difference in temperature between the water and the refrigerant to move the amount of BTUs required. And approach is showing us that we don't need as big of a difference because it is reducing. So the total volume of heat transferred can lower. This can get tricky. I'm trying to be very careful with how I explain this. Let me read. I think of return air to saturation as TD, yes. And I try to purposely not call it approach. That's right, because we don't refer to it as approach in the industry. Like, that's not the way to refer to that. So absolutely. Less CFM equals better heat exchange with water. Hence, so it's not about the refrigerant itself moving slower. It's not about the refrigerant moving slower, like we would think of it in a air-cooled scenario or a air-over evaporator, like an RTU. It's about the total volume of heat is less that we need. And so the amount of approach required reduces. Now, this is if everything is perfect. GPM is great. Heat exchange is good. We don't have any oil issues. We don't have any fouling issues in the evaporator. Like, those are conditions that will give us high approach values. Okay, they'll increase the approach because, again, I don't want to get over, I don't want to go too far with this and then just completely have everybody to lose it. Something like fouling, where we're not exchanging heat correctly, increases approach because to move the BTUs, we have to have a higher temperature difference because there's an insulator, the fouled tubes, the mud or whatever it's gotten in there, the scaling on the tubes is not allowing heat transfer correctly. That's an insulation, which means to overcome that insulation, we have to run a higher approach. The system will naturally run a higher approach in order to overcome that insulator, so that we can still move the correct BTUs to fulfill our goal, which is leaving water set point. Again, I'm really trying to be careful with how technical I get with this. So if I'm losing anybody, I apologize. But if all of those things are not true and we are strictly and all those conditions are correct, and we're just reducing the total capacity on the circuit, then because we have less heat we need to transfer, we don't need as big of a temperature difference. Is that why they say screws are more efficient at lower loads? I'm going to sit on it and try to understand it right. It's going to take some work. Yeah, this is an advanced concept, okay? This is an advanced concept to get your head around, but it's extremely important that you do. Like, as a service technician, you really want to understand this fully. This will become something you struggle with, and it's going to get in your way for troubleshooting if you don't. Yeah. So is that why they say screws are... Well, so all compressors... All right, so it's not quite that simple, all right? All compressors, ultimately, as you lower the load... What's really important is lowering the compression ratio on the compressor. That's what's important for the compressor itself. We want to get a lower compression ratio, which usually when we're unloading the compressor, compression ratio lowers with it, typically, and things become more efficient. Now, there's boundaries to this, right? You can go too far where you're not actually improving efficiency. Now you're just hurting the compressor, and you can go to, like, there's obviously extremes in either direction. And there is this happy zone in the middle where we have the most optimal compression ratio for that particular compressor. And everything comes back to whether it be lift or compression ratio, whatever the case may be, for that. So yeah, screws are more efficient when they unload, and they are more efficient when they're unloading compared to a scroll, for example. We can get far more efficiency out of it than we could other types of compressors. So if we're doing more of a comparison deal, comparing versions, or like from a recip to a scroll to a screw, you're going to get better efficiency out of a screw in part load conditions. By far, in my opinion. Maybe the inverter screws kind of challenge that with permanent magnet motors, but point is, it's not just because of approach lowering and the heat exchange, like what we're discussing, is not the core driver, in my opinion, as to why a screw is more efficient. It has more to do with managing the load on the compressor, not necessarily the heat exchanger. And with approach specifically, we're focused on the heat exchanger, not necessarily the compressor. Any questions on this from anybody? Again, most everybody here is fairly anonymous, so you can ask some what you might think is dumb questions. They're probably not. I can't emphasize, this is advanced material. Like, we're really getting into some deeper stuff here. So nobody knows who you are for the most part. Like, you're not going to sound stupid. Please ask the questions. And again, like, I keep touching on it, but this is the purpose of my certification course. Like, I'm not trying to just shove it down your throat. I'm just saying, like, this is a huge part of what I am doing in that program for as part of the teaching and training. I guess that's why they prefer having two circuits at reduced load rather than one circuit alone. Well, so now you're getting into staging strategies, okay? And there's different concepts to these strategies. Again, this you don't be careful not to get too far off into other concepts, right? So when do we go from two compressors to one compressor, or from two circuits to one circuit in our staging sequence has a lot to do with like minimizing starts and balancing load. And sometimes it is better to have two compressors unloaded versus one compressor, but at some point there's a breakover there, and like that's a very complex conversation in of itself that we would have to, it would take a lot of working through to really explain all of that in detail. You're not stupid, Sterling. How centrifugal X? I'm sorry, I don't understand the question there. Yeah, I'm gonna do a last call on questions on this approach and how this works. Again, I really encourage you. These are things to spend time on in your head. These are things to get straight. As you get these concepts, like, we can get really wound up in trying to think about how centrifugals work and all these things. But reality is, if you can get these concepts here really nailed down in your brain, you start unlocking major understanding on how systems function on a fundamental scale. Is there a difference in procedure for replacing a rear motor bearing on a YK motor on a YK with the motor in place versus motor removed on the ground? Well, I would recommend on that doing both bearings together. I'm not a fan of just doing the rear. If the rear has a problem, so I call that the outer. Okay, that if the outer has a problem, the inner is probably going to have a problem as well, or it won't be far behind. And I would take those motor bearings very seriously, because that leads to a lot of shaft seal failures are from either misalignment or motor bearing issues, causing a lot of extra wear on the shaft seal for a YK. So I just highly recommend, unless it is like a critical emergency. Now, if this is a critical emergency and you can just do the one bearing, then let's see. You've got the rear support. Other than just managing the heavy end bell on the back, because you're probably talking about a smaller motor to begin with, so you're talking about a 300 or 400 horse. You could probably do that on the stand. I've never tried it. I've always been in a spot like, I'm just not doing that. We're gonna do the whole thing. And I've done plenty of bearings like this in the field, and then set them back up there and do the realignment. So you don't have to send this off or anything. But I would highly recommend, like, pull the motor, do both bearings, do a full realignment. Something caused those bearings, and maybe it was greasing, bad greasing practices. That's fine. Like, we need to get in there and clean that stuff up to begin with. Like, I'd really, really recommend doing both. How centrifugal work on low load? How loading and unloading work? Okay, that's a very good question. I will have to get to that question in our next stream, so I'm not going to be able to cover it today. I will add that to I've got that question saved to my list for next week. Um, when you mentioned oil eductors, does eductor mean header? I'm trying to picture what part exactly is that. Yeah, so not an eductor is a form of oil recovery system or part of the oil recovery circuit. Uh, I can definitely go deeper into that in the next stream as well. That one's going to take a minute to work through. We're kind of coming up on time. I see you there from Indonesia. How you doing, bud? Uh, yeah, so high level there on the eductor is it's a jet pump. Okay, so we're getting the oil out of that's getting migrated to the flooded or falling film evaporator. We're getting that back. So you're familiar with a gas pump, Sterling. So it's a alternative method to a gas pump. All right, it's what everybody else does, and is what Trane does on their centrifugals. They don't use gas pumps. They're using uh, they're using an eductor. But I do know, like on the RTAF, the ACR, and the RTHD series, RTWD, all of those have like that gas pump type setup. Um, so we can get into eductors in detail. Yeah, like the gas pump, except just different. We're using it's some people call it a jet pump, but it's just a method of getting that oil back off. Absolutely. Not to slap you again with it, but both here I can show you real quick. So if we come over to let's see. Come over here. Um, so like this is my certification course. We can see that um, the loading process is down here. So I've got this whole lesson dedicated to inlet guide vane loading. This one is with inlet guide vane variable speed. This one is variable speed with a VGD only. This gets into how duplex machines work or multi-compressor. So like this whole set of lessons here breaks down each of those loading and unloading conditions you were mentioning as part of that question. So that's where if you're in the certification course, like that you need for centrifugal loading, unloading, and how the machine manages those loading conditions. That's where you would want to spend your time is focused there. And in terms of eductors, again, if you're in the course, so centrifugals have their own oil cycle, where I go through and I do explain this from a centrifugal standpoint that is part of the oil cycle. I also explain this on the screw side. I've got a whole lesson dedicated to screws with eductors. So again, you can go through and review both of those, but then I have a module on oil systems down right here. So oil systems and management. And in this, I completely break down the eductors for oil return in general. And I go much deeper than I did. So with this one, I'm hyper focusing on just the eductors and not the whole oil circuit as much. But this kind of ties into the other two. So those three lessons as a total all kind of play into each other. So, yeah, exactly. It's a Venturi effect. That's exactly right. You download. Yeah, it is. You can do the certification course can be done from any platform. You can do it from your phone, laptop, tablet, desktop. It doesn't really matter. It fully formats across the board, so you're not limited by device. And the experience you're going to have based off of the device isn't going to change. You're going to get the same experience either way. My point to bringing this up isn't to sales pitch you. My point to bringing this up is if you're enrolled and like those questions and most everything we've discussed today, like it's all in here. This is part of what I teach as part of this. So when we start talking about approach, I have a module on evaporators, and I go not only into each evaporator's design, tube and tube, DX shell tube. So we get into that. We talk about the different approach factors with those. I also have a lesson dedicated to approach in the terms where I explain like all the details to approach values in a chiller here, right? So I'm completely breaking that down in that lesson. That's my point. I'm just bringing up that if you're enrolled, like it's what this course is meant to do. So if instead of waiting for me to get to your question, you can go review it there, and then if you have any follow-ups, you can always come back and we can discuss it deeper. I can try to re-explain it in a better way. Whatever the case may be, that's what it's there for. With that, I appreciate everybody. MTT, make the time for your family, for your spouse, for your kids. Mine are home. I'm sure you can probably hear them off of this mic. This mic does pretty good filtering that, but not so much with this one. So I'll figure out the mic issues. I appreciate the patience. Make the time. Spend time with them. I'll see y'all later.